Good morning students. Today we are going to discuss few topics from chapter 4 moving charges and magnetism. The topic which we are going to discuss is your Biot-Savart law. Now till now we know that whenever there is a current there is a magnetic field. Now this Biot-Savart law gives you the information on which the strength of the magnetic field depends. Now in the figure you see this is your wire through which current I is flowing, and P is a point where we have to define the magnetic field. Now to define the magnetic field at P, what we'll do, we'll take a section of that current carrying element. So the portion which we have taken is your AB, and AB has a length dl, and I is the current flowing through it, and r vector is the position vector of the point P where we have to define the magnetic field due to the current carrying element idl. Okay, so what we will do, we'll try to find the magnetic field at P due to the small current carrying element, and then to get the magnetic field at P due to whole length of the current carrying element, what we will do, we will simply integrate. So Biot-Savart is a person who defined the factors on which the strength of the magnetic field depends. Now as per the Biot-Savart law, it says that the magnetic field at P due to the current carrying wire depends on the current. So as per here what we have written, magnetic field at P, as we are trying to find the magnetic field for a small section of the current carrying wire, that's why magnetic field at P which we have defined by dB is directly proportional to dl. So if you consider the larger length of the element, current carrying element, then strength of the magnetic field will be more. So this is very common. If you take the longer element, current carrying element, the strength of the magnetic field will be high. So dB proportional to dl. dl is nothing but a section of the current carrying wire, and here we have defined that one by AB. Now next factor, dB proportional to 1 by r square. So if r is less, then dB will be more. If r is less, it means what? P is very close to the current carrying wire. Now number 3, dB proportional to I. So if current is high, then definitely the magnetic field at P will be high. Now next factor, dB proportional to sine theta. So theta is the angle made by the position vector with the element AB. So if theta is high, then sine value also high, and accordingly the magnetic field will be high. So these are the factors on which the magnetic field at P depends, and dB is the magnetic field at P due to the small section of the element. Once we get the expression for dB, to get the magnetic field at P due to the whole length of the wire, what we will do, we will simply integrate. So combining this factor, dB proportional to I dl sine theta by r square. So dB equal to k, because we have to remove that proportional symbol. For that we have to bring one constant of proportionality, and that is dB equal to k I dl sine theta by r square. So what we have written, where k is the constant of proportionality. In SI unit, k comes out to be your mu naught by 4 pi. So if you substitute mu naught by 4 pi, you will get the expression dB equal to mu naught by 4 pi I dl sine theta by r square. Now if we simplify this one to represent this one in terms of vector, what we will do, we will simply multiply numerator and denominator by small r. So mu naught by 4 pi I dl r sine theta by r cube. So in vector form, dB vector mu naught by 4 pi I dl vector cross r vector. Idl is your current carrying element divided by r cube. So this is your vector form of Biot-Savart law. Okay. Now the magnitude of the Biot-Savart law is nothing but is your dB equal to mu naught by 4 pi I dl sine theta by r square, and in vector form mu naught by 4 pi I dl vector cross r vector by r cube. So you can say the magnetic field at P, that is dB, is perpendicular to the plane containing I dl and r as per the definition of the cross product. I think you have understood this one. This is your Biot-Savart law, and specialty of this law is that it defines the factor on which the magnetic field due to the current carrying element, the factor on which the magnetic field due to the current carrying element or current carrying wire depends. Now next one is your application of Biot-Savart law. So here what we will do, AB is your straight wire, and definitely current is there. as we have not shown the direction of the current, so let me try to show. It comes out to be your I definitely. So this is your diagram. AB is your wire through which current I is flowing, and P is a point where you have to define the magnetic field. And we have considered a small section to define the magnetic field at P due to the element of that section, and later on we will integrate. So R is the position vector and phi is the angle made by that position vector with the element, and X is perpendicular on the wire from the point P where we have to define the magnetic field. To include the whole length of the wire, we have considered, we have drawn PA and PB, and that one makes an angle theta 1 and theta 2 with the reference line which is perpendicular to the wire, and theta is the angle made by the reference line with the position vector. You can say here we have simplified that one by magnitude only. So R and X, there is an angle theta. Now, as per the Biot law, the magnetic field at P due to the element is nothing but is your mu naught by 4 pi I dl sin phi by R square, as per this law. Now, here simple mathematics we have to apply. So sin phi, if you define, that is your sin phi is your perpendicular by hypotenuse, that is your x by r. And if we define cos theta, that is your base by hypotenuse, that is also x by r. So sin phi equal to x by r equal to cos theta. And tan theta is your perpendicular by base, that is your L by x. So L x tan theta. Now what we will do, we will differentiate. We will take small d on both sides. So x is constant, so there is no variation of x. So dl x d of tan theta. So d of tan theta, you can write d dt of tan theta d theta. So d dt of tan d d theta of tan theta into d theta. I am repeating once again. If you have to take small d on both sides, that is your differentiation, dl equal to x d tan theta. So if you have to differentiate, then with respect to theta, then d d theta of tan theta into d theta, and d d theta of tan theta is your sec square theta. So dl equal to x sec square theta d theta. Now what we will do, these are the part which we have done. Now what we will do, we will simplify this one by substituting it 1. So here dB equal to mu naught by 4 pi I. In place of dl, you can write this value, x sec square theta d theta. So here what we have written, x sec square theta d theta. So mu naught I by 4 pi I dl sin theta. In place of sin theta, what you can write, sin phi. In place of sin phi, what you can write, cos theta, no? Because sin phi and cos theta is identical. What we will do, we will substitute it 1. So mu naught by 4 pi I dl value we have substituted from here. Sin phi is nothing but is your cos theta, and r square is already there. So this one we have done. You try simultaneously doing on the paper. Mu naught I by 4 pi x. So sec square theta, 1 sec theta and cos theta will goes off. So x sec theta d theta by r square. So mu naught I by 4 pi r square x. In place of sec theta, what we will do, r by x. If cos theta is your x by r, then sec theta equal to r by x. So r by x we have substituted d theta. So x goes off, r goes off. So what we'll do, we'll simplify multiplying x dividing by x. So mu naught by 4 pi, mu naught I by 4 pi x, x by r d theta. So mu naught I by 4 pi x, x by r is your cos theta. So mu naught I by 4 pi x cos theta d theta. Now this is your magnetic field at P due to the small section of the current carrying wire, that is your dl, which we have defined by dB, and dB is the magnetic field at P due to the small section of the current carrying wire dl. Now if you have to go for the whole length of the wire, what we have to do, you have to integrate by considering the angle made by this theta 1 and theta 2. Theta 1 and theta 2 is the angle made by PA and PB PB and PA with respect to the reference line X. So what we have to do, we have to integrate. So as the reference line, below the reference line we are considering negative, and above the reference line we are considering positive. So below the reference line is theta 1, so minus theta 1 to plus theta 2. So integration mu naught by 4 I, mu naught I by 4 y comes out, and cos theta is your sin theta. So minus theta 1 to plus theta 2. So integration of cos theta is simply sin theta. So upper limit sin of theta 2 minus of sin of minus theta 1, upper limit minus lower limit. So minus minus plus, so sin theta 2 plus sin theta 1. So this is your final expression for magnetic field at P due to the whole length of the wire, the end of which makes an angle theta 1 and theta 2. If this wire is of infinite long, then what happens basically, A and B reaches to infinity. So under that case, the angle is your pi by 2. Theta 1 and theta 2 becomes pi by 2. It means almost parallel. So for infinite long wire, theta 1 equal to theta 2 equal to pi by 2. So if you substitute B equal to mu naught I by 4 pi x, so sin of pi by 2 plus sin of pi by 2. So this is your 1 plus 1, that is your 2. So mu naught I by 2 pi x. So here is lots of mathematics is there, and you have to do simultaneously when you go through this topic. Take pen and paper and try to do the simultaneously this mathematics part, because it's a simple, but lots of mathematics is there. So if you don't do practice, it's going to be very tough, but once you do the practice, it's become very easy. So this is all about. Please go through and try to find out your doubt. If you have any doubt, please don't hesitate to ask. This is all about. Thank you.